So to start off with, basic radio astronomy, what it is I'm trying to do when I say data processing. So we predominantly do very long baseline interferometry at Warkworth. And basically we have two antennas receiving radio noise from some distant radio objects out there in the universe. We record the data, or we send the data real time over the network, and we bring it to a center that we call the correlator, which you can see down there in the bottom of the slide. And what I'm interested in is being part of doing correlation and further processing, rather than just operating a telescope. Now, the scale of our problem. So, top left slide, you can see our two dishes at Warkworth. We've got the 12 meter and the 30 meter. So that's two antennas, one baseline. Very simple, 300 meters, nothing too difficult there. So on the graph, two antennas, one. 6 antennas, that image is the compact array in New South Wales in Australia. There's actually 6 dishes. The image I took there, the picture, there's only 4 there in the picture. The other one's way out, 6 kilometers away, providing an extended baseline. At 6 antennas, we now have 15 baselines. So you can see how it's scaling. Bottom picture, that's ASCAP. That's the precursor to the SKA that they're building in Western Australia. And there you see 36 antennas. We're now over 600 baselines. And basically, for each baseline, we need one compute node. So the problem scales quickly and fast. Traditionally, correlators around the world, they went out, they bought a big, huge hunk of iron. Incredibly underutilized, very, very expensive. You need people to care and feed. I'm not going to get a research grant in New Zealand to go out and buy a piece of kit like that. And it's a waste of money just sat there doing nothing very much. So, not good. This is where I'd like to push REANNZ. They've been fantastic. They've listened to us. That was the situation before September 2016, 40 gigabits per second coming into the country. That was awesome even then. Most of the international people we work with, they were not looking at those data rates. After September, 100 gigabits. So I'm laughing. I'm really, really happy. I've now got to fill that pipe for them. So that's something I'm working on. But how can we use that 100 gig? How can New Zealand be involved in doing data processing for astronomy? And this is where we started thinking about cloud. Now, this is where I'm getting a little bit more technical, dealing with the data sets here. So, on those images of radio telescopes, I talked about Warkworth. This is another 2-station experiment we did with DiFX in South Africa. So that is very, very long baseline interferometry. But it's only one baseline. 12 scans, 5 minutes. We're talking in the order of half a terabyte. The next one down, that experiment was done using what we call the Australian long baseline array. So you can see the dishes there, the compact array, Hobart, Locust, Savuna, Warkworth and Parkes. And then we've got 15 baselines. And I only took a subset of the data. 1.5 hours, and I think that's, I'm trying to remember now, that's about 4.5 terabytes. So we do deal with big data rates. Just to give you a little bit of science, the experiment with DiFX, as you can see the image on the left, people always like astronomy pictures, okay, they're not quite Hubble Space Telescope pictures, but the one on the left, what we're looking at is what we call methanol masers. So these are highly energetic gaseous clouds in our galaxy where star formation is taking place. And we all know about lasers. Well, we also get other things that do the same as a laser, only in different frequencies. In this case, we call it masing because it's in microwaves. But it's the same thing. It's a natural phenomenon, which I find quite staggering that you can get a natural phenomenon producing something like a laser, in this case a maser. So what we're looking there with the long baseline is we're trying to resolve very small parts of that gaseous cloud. The one on the right, the experiment we did with Australia, this actually led to a Nature paper last year. What we're looking at is what we call a blazar. So that is a galaxy that all of a sudden lights up very brightly over a very short period of time. Short period to us being months. And also in conjunction with this, they detected the neutrinos from this event down in the Antarctic, and that's what led to the Nature paper, the fact that we caught the blazar and they caught the neutrino event at the same time. So traditionally, correlation, what do? We have a head node, receives the data. So on the diagram on the bottom, the things on the left, the data streams, the FX manager, they would normally work on head node. And those other processes we call core 1 to M, which would be equivalent, so M would be our number of baselines. They would be in working nodes. And that's traditionally how we've been doing it to date. And that would all be sat on a humongous piece of iron. Using local servers at Warkworth, I just wanted to benchmark these tests. So this was using the LBA experiment with the 6 antennas. And here I should say speed up is where we say the observation time, so that's the 1.5 hours, divided by the time it takes to correlate or process in the environment. Ideally, what we want to be getting to is at least a speed up of 1, if not better, if we can, because we'd like to do it in real time. So I did it at Warkworth on nothing spectacular, just 2 standard servers, and nothing brilliant about them. And I got to approximately 0.5 speed up. I then tried doing distributed, so we had one of the servers in Warkworth and one of the servers in the city campus. So that's coming down from Warkworth on 10 gigabits into the city, on 100 gigabits, and then out to our campus. Now this is where latency hits us. So our speed up has now dropped down to about 0.3. So that was distributed computing. Just to give you an idea, that's just a graph to sort of show the data flows there. So you can see the data flows coming from our campus, from Warkworth, down through REANNZ and then into AUT. So we're getting about 1.2 gig, which is not bad, but it's latency that's affecting us on that processing. We then looked to see if we could build a cloud-like environment in AUT, because I found out that we had a virtual blade server sat there, which was not heavily utilized. And so we brought one of our big storage array systems down, put that in the city campus, and we just wanted to test, can we actually use VMs? Will they work? Can they handle our compute-intensive and data-intensive processing? It's just an overview of what, it's nothing flash, it's quite a simple little server, 5 blades, 10 gig interconnect between the blades. They're normally running 5 to 6 virtual machines on each blade, and it's running with VMware vSphere version 5.5. So let's try cloud on campus. It works. The VMs can do it. You can see there, by the time we've thrown on the VMs at it, we're up to about 0.8 in speed up. But you'll see on the plot on the right, you can see one of our constraints, and I'll explain that on the next slide. What we worked out is happening is the VMware is trying to share 10 gigabits across all the VMs. It has no way that we can allocate dedicated bandwidth to just my VMs. It's trying to load balance. So even though the other VMs are particularly busy and not using much of the network, it's still trying to reserve bandwidth for them. And so as you can see there on that plot, as I added more nodes, my bandwidth is slowly going down. And that's what's holding me up in this environment. This is where we went out and we had a chat with our friends at Catalyst. I have a disclaimer here. I have no commercial interest in Catalyst. I'm just a very happy researcher who found a very willing and capable and able partner to work with us on this project. So I've got a few slides here from Catalyst that they provided. So first of all, their centres, where they're based. So you can see they've got a centre in Hamilton, Ororua, and Wellington. Now, the nice thing is they have worked with REANNZ, and we have, not just me, but all of you, we have interconnect between REANNZ and Catalyst on a dedicated network link. So we're not competing with anybody, we have a dedicated link between ourselves and Catalyst, which is great. I'm not up with their hardware technology. They sent me this slide, so just to give you an idea of what their servers are looking like that sit in their chassis and their storage array system that they've got. I can't really say much more about it. That's sort of underlying hardware that Catalyst are running. And the nice thing is this, I don't have to worry about care and feed, the capital costs, etc., etc. That's handled by the cloud service provider. And of course, they will be upgrading stuff as time goes by. I don't have the upgrade costs, the upgrade cycle to worry about. That goes with them. Now, we moved what we had in the AET environment and we put it into the Catalyst environment. And first of all, can we correlate the data? I'm not trying to get any speed up. It's like, does it work? Do I get, in my terminology, what I call a fringe? And that top plot, the red spike, that's what we call a fringe. And that's when radio astronomers, or certainly VLBI radio astronomers, jump up and down and get all excited. So we have the signals correlated. They're in phase, we've adjusted the time, we've adjusted for the Earth orientation parameters, we've got the two signals coherent. Bottom right, that plot, that's just showing us recovering the radio band, or bandwidth between the two antennas. So this worked, and this is Warkworth and Hardy style. So I'm confident that this works. I'm pleased. Fringe quality is 5. Would have been nice to get 8. We go from 0 to 8. Don't know why, it's historical. But the signal to noise ratio is really good. So we've got a good fringe there, and we can do some science from that. Taking that two-station experiment, I was experimenting with to see if different storage technologies on the cloud, different file systems on their storage technology made much difference. So I've got ext4 file system, and I created a RAID 0 file system within their storage array system. Yes, for a small number of processors, it does make a difference, but once we're over 5, it's marginal. It's not really making much difference. Next, we're taking the 6-station experiment. We're throwing compute nodes at it, worker nodes, and seeing what we get up to. And what we're seeing here is we're plateauing out at about 14 compute nodes. So there are other factors at play. There's still more things to be looked at and investigated in this. But the point is, the cloud works for what I want to do. I've got to speed up at 0.6 in this particular scenario. Now, I want to talk about technology that I was introduced to by Catalyst called Ansible. It's a scripting language, and it allows you to build VMs, break down VMs, customize VMs, do your network, change your storage, do your NFS mounts, etc., etc. And we found that this is really, really good. What I do is when I do an experiment, I get for the experiment of X files, so I know how many antennas are involved, I know how many baselines, so I can work out how many nodes I need. The other thing we thought about is with this, with the cloud, could we actually break the problem up? Can we sort of almost parallelize it, say, based on time? So if I have a 12-hour experiment, can I break it into 4-hour chunks? And take out each 4 hours and give it to a different head node. Can I break the problem out that way? And of course, Ansible allows us to do that. So with the work, a gentleman called Glenn from Catalyst, we worked on that. So he wrote the scripts and we did some testing. So top left is my idea of how we would break the problem out. Bottom right is off the console of Catalyst, showing how it's taken that problem and it's generated all the appropriate nodes for us. And here's just to show Ansible working. So at the top there, those are all the nodes it's created, so I can see all the instances. And then down below, it's just basic HTOP showing CPU, memory, etc. And I can see all the DiFX processes. It's too small for you to see on there, but if you sort of look on the top of those CPU utilization ones, you'll see there's a whole load of processes sat at the top called MFX core, and they're running flat out. So it scales out, it runs nicely, and that's great. So what we're looking at and what we're discussing with our community is, can we shift how we think about data processing for radio astronomy? On the left, we've got the antennas sending data via REANNZ to a central correlation site, where they have a humongous RAID storage system. They have a HPC cluster. They process it, they correlate it, they generate the final data product. The data product goes back through the network to an analysis. It can be set anywhere in the world. what we're talking with our community is, can we change how we look at that? Can we move all that into the cloud? So, the figure we've got down there, in the right-hand plot, the little red lady, she's the correlator person. She's the person doing the correlation. But she doesn't need to be physically where the correlator is. On the right-hand side, we've got the analysis. He doesn't have to physically be where the data is. So this is something we're working on within our community to try and implement. Just to give you a comparison with dedicated HPC hardware, so at the top there, we've got the Porzo Supercomputer Centre in Western Australia, Magnus. You can see they threw 288 cores at the same experiment I did, and they got a speed up of 4. The next one down, we've got Bonn, Germany. They threw 480 cores, not exactly the same problem, same experiment, but similar sort of size, and they got a speed up of 5. So out of the box, not doing anything, we got 0.6 in the cloud. Using the Ansible idea, we've now got up to 1.2 speed up factor. So that's faster than real time. So at that point, that's good, and I'm happy. And now we need to work on if we can push that a little bit higher. But the point there is that we are not that far behind HPC by using the cloud. So what I like to say in summary is, yes, we can correlate in the cloud. We're not far behind HPC computing. Yes, there are trade-offs to going to the cloud. But in terms of the flexibility of being in the cloud, creating nodes on demand, doing my processing, and then tearing it all down at the end, and not having something running and incurring cost, I think it's quite advantageous. And would certainly help with my budgeting. And what I'd like to do is end with a nice picture of New Zealand. Thank you very much, everyone.